Welcome to this presentation on making resilient models by Group 67 Transformers, based on this paper by Liu et al. What is the problem this paper seeks to solve? The problem is that ML models usually work well only when they see data, which is like the data on which they have been trained. If the data distribution changes over time, the performance of the model often deteriorates. For example, a surveillance camera trained to work on sunny days will work well on sunny days, but might fail in poor weather and in bad lighting conditions. What solutions to this have been tried previously? The first solution is domain adaptation. Domain adaptation is a learning paradigm where a model is trained on a source domain and adapted to perform well on different but related target domains. In DA, we need to train the model on labeled or unlabeled target domain data as well. So what are some issues with DA? The source domain needs to be stored in the memory in conditional DA, though source-free DA attempts to solve this. Performance before and during the unfamiliar period is poor. Only after the training does the performance improve in DA. So we need a model to work well even during the unfamiliar period. The next solution is domain generalization. DG is a learning paradigm where a model is trained to generalize well to unseen domains without having access to them during training. There are also some issues with DG. Existing DG methods are typically based on accurate supervision knowledge of the source, and it might not be available in all cases. When DG is applied to scenarios with continual domain shifts, as DG focuses more on the target domain, there could be severe catastrophic forgetting of domains that have been learned. So we definitely need a new solution. So this is the author's solution, the RATP framework. The goal of RATP is to improve model performance before and during the training stage of each previously unseen target domain, that is, in the unfamiliar period, while also maintaining good performance in the time periods after the training. So these are the three things that the RATP framework achieves. A good TDG performance, which means that the performance is good before and during training on unseen data. It has a good TDA performance, which means that the performance is good right after training. It has a good forgetting alleviation performance or FA performance, which means that the performance is good on the old domain even after seeing newer domains. So this is an example of an accuracy matrix, this graphic in the corner. For each domain, the TDG is the mean of the green elements, the TDA is the mean of the red elements, and the FA is the mean of the blue elements. Let's see how the problem is formulated. A labeled source dataset S is assumed. A sequence of continually arriving unlabeled target domains T is present. The label space is constant across S and T, and the target domains arrive in a random order. The generalization performance for the Tth domain TT depends on both the previously seen T-1 target domains and the original source domain. We also store class exemplars closest to each class centroid for each domain in S. The model is a deep neural network, feature extractor f theta at the bottom and a classifier g omega at the top. For each domain, its current model and the inherited model from the last domain is stored. So let's now start with the first component of RATP, which is random mix-up augmentation. RandMix augments the source domain S with new artificially generated data. These are the goals of RandMix. It seeks to enhance cross-domain transferability, maintain order-agnostic generalization for low-quality domains, training free design of autoencoders, balance randomness and generalization by injecting noise with smaller variance, avoid error propagation by selectively augmenting high-confidence target samples. Now let's see the RandMix process in depth. First, we initialize simple autoencoders. The encoder and the decoder are randomly initialized from a normalized distribution. Next, we introduce noise using ADA-in. Then, we mix the noisy samples using random weights generated from a standard normal distribution. We scale the mixed value using a sigmoid function. Lastly, when applying RandMix to a target domain, we augment only the high confidence predictions to ensure that we don't recreate possibly wrong data. Now we move on to the next aspect of RATP. For the target domains, we have just the data, no labels. We need to create the labels ourselves. There are some challenges with the earlier softmax-based pseudo-labeling and short methods, as you can see here. So clearly, the authors thus propose a new method T2PL to solve these issues. T2PL helps in generating more accurate pseudo-labels. Now let us look at the T2PL process in depth. Firstly, we use the softmax confidence to select the top 50% of samples per class. Then, we compute the centroids using predicted weighted aggregation, using only the top 50% of samples. Then, we select the top half of the samples with the highest similarity to the centroids. This ensures that the most relevant samples per class are selected. Finally, we use the refined samples to fit a KNN classifier and assign a pseudo-label. The authors only select the top 5% of the samples for this. With such good filtering of the data, the pseudo-labels are much more accurate than other methods like short. On this slide, you can see that the goal of PCA is to align the domain-specific prototypes to improve model generalization across domains, addressing variability and insufficiency in data. Of course, there are some challenges in PCA which you can see on this slide. Firstly, the authors use linear layer prototypes where they use the neural weights of the classifier as the prototypes. Here you can see the formula of the cross entropy loss, whose goal is to try to choose values of the prototypes which fit the current domain best. Now let's look at the next aspect of the PCA process, which is contrastive alignment. With PCA, we aim to make sure that the new prototypes take into account the prototypes of the previous domain as well. This is included in this loss called the PCA loss. This is the expression of the PCA loss. The PCA loss is trying to make sure that the class prototypes across the domains are similar. As a final addition, we also add a knowledge distillation loss. This loss helps to prevent forgetting by transferring knowledge from the stored old model to the current model. So finally, the term of the expression of the loss is given by LCE plus LPCA plus LDIS. Note that LDIS is not used in the source domain loss. So this is the overall view of RATP. This is an example of a problem which RATP would be able to solve very well. Consider this particular class of giraffes. In the source domain, the images are real photographs of giraffes, while in the first target domain, they are artistic depictions of giraffes. Here, RATP will give high performance during unfamiliar period. Now, as you can see in the results here, there is definitely an improvement in the performance. In the last table, the RATP clearly has the highest performance in almost all the cases. The authors also did ablation studies. The authors showed that removing any of the rand mix or T2PL or PCA from the model reduced the TDG, TDA and FA accuracies obtained on the digits dataset. Thus, all of them would be substantial improvements to a model without them. Okay, thanks for watching.